Welcome back to ECE 320A. Homework number 4 is not yet on D2L, but it will be shortly. So I just need to make sure it happens. Final exam, does that look about right? Is anybody, so it's starting at 10:30. You will have to get here 2 hours before the normal start time of the class, and it is on a Tuesday, May 8th. Your final exam then is 10:30 to 12:30. We will have one more homework assignment after homework number 9 is the plan. Homework number 9 will be on Bode plots and maybe some filtering. And we will figure out what homework 10 is when we get that far into the future, which is maybe in a couple of days. What I want to do today is go over a Bode plot example that tries to illustrate what we were working on or talking about with respect to the individual terms in a transfer function on the last time we met. Then we will have a 75-minute quiz in the remaining hour of the class, just for your pleasure. No, that's an in-class participation problem, and I want to see, did you follow what I've said in the last lecture and in the first part of this lecture on Bode plots? Can you actually create a Bode plot given a transfer function? Can you do it by hand? Can you sketch it? That's why you need to pay attention on this first round when I'm working through the example. Then we will get into filtering, which passive filtering is in Chapter 14. You've already looked at finding some transfer functions for circuit diagrams. Those create filters. And I think with the Bode plot material, you should be in a much better position to understand frequency response and how you could even design filters based on what your knowledge of Bode plots is. Meaning, well, we'll get to that point when we get to filters. Let's look at an example. And let's say that our transfer function that we want to sketch the Bode plot for is given as 10,000 s plus 0.1 over s plus 100. What structure or form would we term that transfer function expression is written in? What terminology would we express that? This is a pole zero form. And that's not the structure that we need in order to sketch the Bode plot. We want to be able to add all of the individual pieces that we sketch independently. At the end, we want to add them all together. And because of that, we want to normalize these constant coefficients to a value of 1 so that the gain gets accounted for from the very beginning. In order to do that, we can simply factor out all of these constant coefficients. We have 10,000, that's a gain-like term, but now I will go ahead and keep that 0 that's located at minus 0.1 explicitly identified by putting it right underneath the s, or what's the time constant of that factor? 10, right? It's tau s, where tau is what multiplies or scales the s, and tau is 1 over 1/10, or 10. Then we have our pole at the origin, and we have our other pole at 100, and we have then a real pole and a real 0. We have a pole at the origin, and we have a gain term. We now want to combine all of those gain pieces together, and the 100 in the denominator cancels a couple of those zeros. This, whoops, well, it's okay. That 0.1 cancels another 0, and we're left then with the following transfer function description for h of s. It's 10 s over 0.1 all over s over 100 plus 1. And this now is in the form that we want in order to sketch the Bode plot. And that's our time constant form. And we really are not looking at h of s for all values of s. We want to specialize this to sinusoidal excitations, or we want to look at what this transfer function looks like when we're walking along the imaginary axis from 0 up to infinity, or j infinity. So we're starting at j0 dc and walking all the way up the imaginary axis, which means that really what we are doing is looking at h of j omega, and h of j omega is then a complex number. It being a complex number says that it has a magnitude and a phase, and those are really the two components that we will worry about in trying to make these sketches. And now if somebody was more verbal in their way of learning or thinking, what I sometimes like to do is actually, before I even sketch this or start the sketch, I like to actually provide a word description of what I'm expecting to see. Meaning I'm going to talk my way through each of these terms. I have 4 different terms. 2 are linear terms. I have a real zero and I have a real pole. I have a term that's associated with something at the origin, and that's actually a pole at the origin. And I have a gain piece. And if somebody said, what's the DC gain? What would you say? Trick question. It's infinite, isn't it? Because we have a pole at the origin. So this gain hanging out there is not really the DC gain. This gain amplifies or shifts the whole transfer function up, but it doesn't really overcome what this guy is doing at low frequencies. This pole is causing everything to get really, really big when omega gets really, really small. Does everybody see that? So asking for the DC gain is the trick question on this. It's actually undefined. It's infinite. And now you could still do the initial value theorem on this transfer function. I like to go back to this form if you were doing the initial value theorem. As long as the limit exists, and it will, in this case, you multiply h by s. And can you apply the final value theorem on this? You are looking at the poles of s times h of s. That s cancels that pole at the origin. So as long as you just have that one pole at the origin, h of s is well behaved, and you can apply the final value theorem to this particular problem. That's not associated with the Bode plot, but that's something that you need to know by the final. Here's then a word description of the Bode plot for this particular transfer function. I'm going to look at the 4 different pieces independently, and because of that, or the reason I'm able to do that is because we're talking about the magnitude in dB and the phase in degrees, and then once I've put each of these individual parts onto my graph paper, I can sum immediately all the contributions from each term because of the dB fact of the magnitude and the angle of the phase relationship. Those are all additive type operations. The magnitude of the constant term is simply 20 times the log, and this is log base 10 of 10. Log of 10 base 10 is 1. That particular gain factor simply will adjust all the remaining pieces up by 20 dB at all frequencies, and I might just say 20 dB for all omega. That's flat. That's not sloping or anything. It's just a flat 20 dB. And what's the phase? This was a positive 10, and that will then contribute 0 in terms of our phase for all frequencies. Let's now look at the second piece. And for whatever reason, I decided to look at the origin term next. The magnitude piece, what do I know is sort of special about poles or zeros at the origin? If I now, well, let's just look at, well, no, I'm not going to do the expression. It never breaks, does it? It never stops. It's always on. If I have a pole at the origin, it's going to be really, really big at low frequencies and really, really small at high frequencies. And that line, if I just have one pole at the origin, the slope we know is 20 dB per decade down, or minus 20 dB per decade. And it's always sloping. There's no break or kink in that term. Likewise, if I had a single zero at the origin, it would be in the other direction as far as its slope. It would be really small at low frequencies and really high at large frequencies. But because we are only looking at this term in isolation, we can actually pin it down as far as where it's at. This is now a straight line with a slope equaling minus 20 dB per decade. And we need to basically say where that is or how we can find it on our graph. It will actually pass through 0 dB at a frequency of 1 radian per second. That's what the magnitude does. That's where we can pin it on our plot. Is we know it's a line that slopes at minus 20 dB per decade. We can fix it on our graph by locating one of the points on that line to be 0 dB at omega equal 1. What's the phase of this single zero? I'm sorry, this single pole at the origin? We're talking about this term, and if I said, okay, the angle of j omega, if I just said angle of j omega, you would say, oh, that's 90 degrees, but since it's downstairs, it's a minus 90. And it's always on. In my word description then, I'm just going to say that I have minus 90 degrees for all omega, and that's pretty easy to sketch. I just have to draw a horizontal line at minus 90 degrees for that component. The next term that I'm considering is the single zero at omega equal to, or its break occurs at omega equal to 0.1. Or you could say, maybe I should say, this is now this 0 at s equal to minus 0.1. But we're sketching this for positive values of omega, so we don't have to worry about it being written, or the s equal minus 0.1. It's critical that it's there, but once we know that it's there, we really are only concentrating on the frequency now, omega equal to 0.1. If we want to sketch its magnitude, what do we know about it? This is now a linear factor with a constant, and because of that constant plus 1, this one will break. And for low frequencies, and by low frequencies I'm meaning a decade below wherever this breaks, this one's going to break at the corner frequency 0.1. A decade before that, we simply multiply that frequency by 0.1, and we now know that for frequencies less than 0.1, we can approximate this complex number by simply the real piece of that complex number, which is 1. We take 20 log of 1, which is 0. We know we're at 0 dB for small frequencies, omega. We also know for large frequencies what's going to happen. If omega is bigger than a decade beyond 0.1, then the imaginary piece of that complex number dominates, because it's now like 1 plus j10. The complex part dominates. We can now say, oh, that's just 20 log of omega. And it's actually, because it's a 0, it's going up at plus 20 dB per decade. And we have it flat for small frequencies. We have it going up for high frequencies, and where those two intersect in our straight line approximation is right at the break frequency. And the way I verbally communicate this is I say, oh, I have this piece, which is 0 dB, this line, until omega equal the break. At that point, this line breaks with the slope equal to plus 20 dB per decade. And that's how I could verbally express what's going to happen when I sketch this linear factor. It's flat at 0 dB until I reach the break, and then I'm going to go up at plus 20 dB per decade. What's the phase look like? Again, I picked these 3 different frequencies. The most I can ever get out of a single linear factor is 90 degrees. It'll be plus 90 if it's upstairs, minus 90 if it's downstairs. It's going to be approximated to be 0 a decade before the break. It will be right at plus 45 degrees, since it's upstairs, since it's a 0 at the break. And we'll consider it to be 90 degrees for all frequencies bigger than the frequency 1 decade beyond the break frequency, which is going to be at 1 radian per second. And really all I'm doing now is connecting those 3 points. It's going to be this phase of 90 degrees, this transition from 0 degrees to 90 degrees happens or occurs over a 2-decade span. And that 2-decade span is centered on the break frequency. And prior to that 2-decade span, it's 0, and beyond that, it's plus or minus 90, being whether it's a 0 or a pole. And these are just single pieces. Let's now look at the last piece. And this piece is just like what we did for the single 0, except now we have to simply think about where it happens, which is this single pole at minus 100 radians per second. It's this real pole out in the left half plane at minus 100. The magnitude, if I do the same thought process, it's going to be 0 dB until omega equal what by our straight line approximation? Until we get to the break frequency, which is 100. Beyond that point, or at that point, it's going to break. And what's our slope beyond omega equal to 100 radians per second? It's now downstairs, it's a pole, so it's going to be going down at minus 20 dB per decade. As we did with the zero piece, we can do the same thing with the pole piece, except now we're going exactly in the opposite direction with our phase. It will be 0 a decade before the break, which in this case is 10 radians per second. It will be minus 45 right at the break frequency of 100, and it will be 90 degrees a decade for all frequencies beyond a decade above the break frequency, or above 1,000, or 10 to the 3. That's my word description of this Bode plot sketch that I now want to try to generate. So let's now look at the plots. And the first plot that I will do will be our magnitude. Here's my axis. Let me say this is now 10 to the minus 3. How many cycles do I have on that sketch? Why am I counting 6? Am I missing one? Is it a 6 cycle? So I'm just looking at the decades that are here. So I have 1, 2, 3, 4, 5, 6 cycle is my paper that I've created. And ideally, you could have semi-log paper to make these sketches with. If we remember what we were working with before, we now go back and we say, okay, now let's put each of these on there, each of these individual pieces on there. The first piece is the constant term, and I need to now sketch that at 20 dB for all frequencies. And now I'll just say that this is the 20 dB point. And this is due to the constant term. And that was term number 1, I think. Let's now go back and look at term 2. That was our single pole at the origin. That's now this line that's sloping minus 20 dB per decade. And it passes through this point. This is 0 dB. It passes through 0 dB at omega equal 1, or 10 to the 0. Meaning if I do this correctly, it should be at plus 20 dB before that, and it should be at minus 20 dB above that, and everywhere else it's at that same slope. So really you should be getting out your ruler and making these sketches much more accurately than I am. But that is due to piece number 2. Piece number 3, we are 0 dB until we hit omega equal to 0.1, and then we start sloping at 20 dB per decade, and we never have to shut that slope off. So now we need to find point 1 on our diagram, which is right here, and at that point we need to, or from that point on, we need to be going up at 20 dB per decade. So this is due to piece number 3. It was 0 dB until we reached that 0 factors break. Then the final piece, piece number 4, or term number 4, occurred at 100. That's over here. Whoops. And we're then down at minus 20 dB for the decade beyond that. And so this piece goes down at a slope of minus 20 dB, and this is now term number 4. Now what do? I have all of these individual pieces sketched or indicated on my diagram. Now what I need to do is at each frequency, I look at the vertical line, and on that vertical line, I add up all the pieces that are occurring at that frequency. Meaning, if I have this sloping line due to the pole at the origin. But everywhere I'm going to adjust every point by 20 dB because of that constant, which means that back here at, let's say at point 1 right here, I have a contribution due to the 20 dB, and I have another contribution due to the the pole at the origin of 20 dB, so I should be at 40 dB at that frequency. If I look back earlier in frequency at 0.01, I now have 20 dB plus 40 dB, or I should be at 60 dB. Is that making sense? I'll try to sketch this then in red, meaning I just said that I have 20 plus 20, that should be 40. Here I have 20 plus 40, or 60. So this should be parallel to the number 2 line, but offset by 20 dB at every point. Meaning, and it will look like that until I reach this point where I start having that 0 slope introduced. Meaning I'm going to be coming down at 20 dB per decade until I reach that particular frequency. At that frequency, what happens? I was going down at minus 20 dB per decade. At omega equal to 0.1, what happens? Well, I introduce another piece that's going up. So now my slopes exactly cancel. And if I don't have any slope, I'm going to be flat. Is that making sense? So now I'm going to be flat at 40 dB. The reason I'm flat at 40 dB is because at omega equal to 0.1, I have 20 dB contributed by the pole at the origin. I have another 20 dB because of the gain of 10, which converts to 20 dB. So I'm at 40 dB total at omega equal to 0.1. But beyond that, I now have no slope until I reach another break. And the next break, and sometimes what I like to do is I like to sort of look at this diagram and say, oh, I'm going to have something magic happening there. That's where a break is going to occur. And I'm also going to have something magic here. And I'm drawing those arrows up and down for a reason. I was coming down at a minus 20 dB slope to begin with, and then I changed my slope by plus 20 dB. So I have 0 dB slope until I reach 100. And at that point, I have down 20, up 20, down 20, or a net down 20. Meaning at 1,000, I better be 20 down from where I was. And remember, that was our Vegematic. We set it and forget it or some such thing. The slopes and the magnitude, once the magnitude breaks, you never have to turn it off. It's always on. Is that making sense? And that red line then is what MATLAB should generate for you if you plotted the magnitude plot. Now this is an approximation. MATLAB would give you the exact answer, or PSpice. If you did a frequency response of this transfer function, you should expect 40 dB of gain at omega equal to 1 radian per second. And what's 40 dB of gain in absolute terms? You take 20 log of x is equal to 40. So divide 40 by 20, and now you have log x is equal to 2. So what is 2 when you take the base 10 log of it? 100. So this is a gain of 100 at omega, where it's flat. Prior to that, the gain is bigger, and after that, the gain is less. Is that making sense? What's the gain in absolute terms at omega equal to 1,000? Or, okay, what is the gain in dB? 20 dB. So converting that to absolute, you have 20 log x is equal to 20. So log of something is 1, 10. So you have a gain of 10 at this frequency, and you had a gain of 100 at this. Remember, this is a dB scale. So this linear distance means quite a bit of change in terms of absolute value of your gain. Will you have a gain of 0? Well, you will have, at what frequency will you have 0 dB gain? At 10,000. It's still on it's not on my paper, but at 10,000 or 10 to the 4th, you're going to be another 20 dB down from where you were 20 dB. You'll be at 0 dB at 10 to the 4th, or at 10,000 radians per second. What does that mean, 0 dB? A gain of 1. So now you inject a signal, and now here's another thing that'll be the final exam question. You've now sketched this Bode plot, and somebody says, oh, what's the response if I inject a sinusoid into this system? Meaning, if I now put in a sine wave, or let me put in a cosine wave, I say put in a cosine, let's just say it's 2 cosine of 1t. What's the output response going to be in the sinusoidal steady state? This tells you for all frequencies what's going to happen. You say, oh, what was the frequency again? 1 radian per second. You find 1 radian per second. Now you look and find, where's my magnitude at that particular frequency? And you go up and you say, oh, it's 40 dB. Well, I need to convert that back to absolute terms, which we just determined was 100. So this particular circuit is going to amplify those signals coming in at 1 radian per second by a gain of 100. So you're going to see 200 cosine of 1t plus, that's why we need to plot the phase. So this is the magnitude plot, but once we have the phase plot, you can find the sinusoidal steady state for any frequency that somebody gives you. You don't have to do it point for point in the S-plane. Is that making sense? And that's why these are basically insightful diagrams, because it tells you a lot. This is now the magnitude of h in dB. Let's now look at the phase. Well, are there any questions on this magnitude plot? Do you see how much data or how many questions I can give you just based on this diagram? I could give you one question on the final that would be comprehensive, and it would be so easy to grade. because I would make it challenging enough that maybe you'd get stuck on the first part, and then I say 0, 0, 0, 0. Any questions? But there's 1,000 questions you can have about this, because I could ask for 1,000 different frequencies, couldn't I? You now know a lot about the magnitude response of your system. If somebody said, oh, what's this filter? It doesn't really have one of our generic descriptions. It favors low frequencies, doesn't it? It really amplifies low frequencies. So it's acting like an integrator at low frequencies. Then it flattens off, and it really pretty amplifies low or mid-range frequencies from 0.1 radians per second up to 100 radians per second. That's a gain of 100. And then it starts rolling off at high frequencies. And that's probably a good thing, to roll off at high frequencies, because you don't want a bunch of noise being amplified. And the noise is at higher frequencies. All right. Let's look at the phase plot. Remember, you have a quiz coming up. So you need to be able to reproduce this for another set of transfer functions. Here's now, and ideally, you would line up your, oh, wasn't that good? I don't know if you are impressed as I am with that, but I had already scrolled beyond the diagram, and I still located 10 to the minus 3, pretty close to where it is in the top one. So you want to align your diagrams, your axes. It doesn't take much for me to get excited. All right, you didn't have to agree. There is our frequency axis. And we go back and we say, okay, now I'm looking at my phase half of these descriptors. And the gain piece is easy. You'll get 20% of 5% of 10% of the right answer by answering that. You're going to have 15 problems on the final. So just to prepare you for that. But the gain piece, I don't have to even sketch. I just sketched that already with my axes. The next one, the single pole at the origin, you better be able to sketch these. Just pull out your ruler and draw a straight line, and you've already now, and make sure it's at minus 90 degrees. You've now sketched the piece of the phase contributed by that pole at the origin. It's always contributing minus 90 degrees. So if I come down here and I say, okay, here is minus 90 degrees, this was due to term number 2. Now what happens? Now I go and now I have the more interesting pieces. Because now when I have linear or quadratic terms, I have to worry about turning on the slope and turning off the slope when I'm dealing with phases. So not only do you have to worry about turning them on like you do in the magnitude, you now have to shut them down. So in this one, I need to turn it on a decade before the break, and these slopes are distributed across 2 decades of frequencies. And that 2-decade span is centered on the break frequency. Here your break is at omega equal to 0.1, but we need to go back to 10 to the minus 2 and turn it on. So now here is where we turn it on, here is where we turn it off. And we should get to plus 90 degrees after a decade above the break frequency. Does that look right? What about the 4th term? Now our break is at 100, but remember, this starts a decade before. So we need to turn it on at 10 and turn it off at 1,000. And so sometimes with this, I might say something like, oh, I need to turn this one on and turn it off. And then over here, I need to, where was my break? It was at 100. I'm sorry, my break frequency was at 100, so I need to worry about it kicking on a decade before that. And this is a pole, so it's going to initially be down for the slope. And then I'll have a change in slope of shutting it off. And that sort of gives me some guide markers as to what to do. So that now I'm looking at turning it on here and turning it off there. And you kind of have to be careful because now things are overlapping. Those are actually on top of each other, but I'm exaggerating the spacing so that you know that there's two things now at minus 90 degrees beyond 1,000 radians per second. And because these are angles, now we can add them up term by term or frequency by frequency as we go from low frequencies to high frequencies. So at low frequencies, what's my phase angle? Minus 90. So now if I said, oh, look at the sinusoidal steady-state output response, and you inject, and I'm going to say I inject an input cosine, I'm going to say x of t is equal to 2 cosine of 0.001 t. And now I say, what's the phase of the output response in the sinusoidal steady state? Your output would be something, what did I say the amplitude was? Just 1 to begin with, cosine of 0.001 t. Where's 0.001 t on here? 10 to the minus 3. The phase is going to be adjusted by an angle of minus 90 degrees. So now my argument of the output would be cosine of 0.001 t minus 90 degrees. And if I wanted to know how the amplitude was scaled, I would now need to go back and say, oh my, it's going to be huge, isn't it? So what do we have? We had 40 here, didn't we, by this piece? So I'm just going to go this piece and then I'll add 20 to it. So I had 40 here, 60 here, plus 20, 80 dB. Ooh, 10 to the fourth. So you now have 10 to the fourth cosine 0.001 t minus 90 degrees. So if you had to sketch those, your output would be huge, but it would be shifted 90 degrees relative to the input waveform. So it's now going to have a time shift. Is that making sense? Now let's add all of these pieces up in our phase. We now are going to be minus 90 to begin with. Then at that point we start adding a positive slope of 45 degrees per decade because we go through 90 degrees over 2 decades. Meaning at this point I would be up to minus 45, and by this point I would be up to 0 because I have now minus 90 plus 90. And it gets really interesting when you have your 2-decade spans overlapping, because then you have to turn something on, turn something on, turn something off, turn something off. You have to keep track of all of that. Is that making sense? Now what do I do? I'm not sloping anymore, am I, for a while, because everything is flat. Now I start sloping again. And I start sloping. And what you can do is you can say, okay, does this make sense? I say, look at this red resulting curve, and I say, does that minus 90 degrees at high frequencies make sense? Well, I have plus 90 due to the 0. I have minus 90 due to the pole at the origin. So those cancel. but I have another minus 90 due to the pole at wherever it was, 100. So yes, I should be at high frequencies minus 90 degrees. And you could have actually, I could have asked you what's the phase at high frequencies in this particular circuit, and you should be able to tell me immediately. Because you know the denominator is going to contribute 2 minus 90s. So minus 180 due to the denominator, due to your poles. You have two poles, each contributing minus 90, and you have one zero contributing plus 90. So at high frequencies, when all of these are working, when S is getting big, you're letting S go to infinity, so to speak. Now you have plus 90, minus 180, or at high frequencies, you should be at minus 90 degrees. If I ask you the opposite question, I said, what's happening at low frequencies in the phase? You can say, oh, let me see if I have anything at the origin. He's trying to trick me here. Well, you do. You have a pole at the origin, and what does that do? That always contributes minus 90 degrees. Is that making sense? So you started at minus 90, you kind of come up, and then you go back to minus 90. And if you looked at this phase plot, somebody could say, where is my input cosine going to be lined up with my output in the sinusoidal steady state? For what frequency range? From 10 to the 0 to 10 to the 1. From 1 to 10 radians per second, my input sine wave will be lined up with my output sine wave in the sinusoidal steady state, right here. Is that making sense? Everywhere else, there's going to be some phase shifting going on. And what's my amplitude? Between 1 and 10, my amplitude was constant, but it's a gain. It's a pretty high gain, isn't it? It's 100. So things will be scaled by 100, but they will be lined up. And so now if you're looking at the peaks and the valleys, or the maxes and the mins of this cosine, and those are going to be going at 1 radian per second up to 10 radians per second, and the input will be scaled by 100, and they will all be aligned in time. The peaks will be with the peaks and the mins with the mins. Questions on that? And you can tell a lot about what your system is doing from the Bode plot. And what I want you to be able to do is pull out a napkin and sketch these. If somebody, you're having a nice relaxing meal with someone, and they start talking frequency response and Bode plots, and you go, let me give you a transfer function. And you give them a transfer function, they go, what are you talking about? Oh, let me show you here. And you just start sketching the Bode plot. And they go, oh, that looks familiar. I've got that in my living room. And you go, what? They aren't lying. They might have a graphic equalizer on their stereo. And that's now how they've set their dials. They now like the bass, so they've really accented the bass, so they've got their dials up at the low frequencies, maybe the mid-range, they okay with some vocals, but then they really don't like that high frequency, so they've got it really blocked. And you go, exactly. That's what I'm sketching, is a graphic equalizer, a Bode plot. So now you can show me if you can do this. Here's your quiz. Now, show me that your summer internship is going to be fruitful, that you can now tell your colleagues what this is going to look like frequency response wise. And we'll scale this by minus 20 dB, the time allotment. I said 75 minutes before. A minus 20 dB reduction or change will now be a tenth of that, so you now have 7.5 minutes. See how you can use all this stuff? Oh, that's just 3 dB, up or down. And that's your half power frequency. I'll be quiet so you can concentrate. We've used up our minus 20 dB of time. Did everybody get finished? No? We're slow. I actually tried to do this. What kind of a filter is it? Did anybody get the magnitude response yet? Does it have a shape that looks reminiscent of any kind of filtering action? Pardon? So what's it doing at low frequencies? It's cutting them off. So the magnitude response is small at low frequencies. Is that true? And why is that the case? Because of this guy at the origin, which is a 0, right? So we have a 0 at the origin. And what does that look like in terms, if we just looked at that by itself as a piece? It's always on, isn't it? But if you said, okay, now for small frequencies, replace this with j omega. And now at small frequencies, that's small. At big frequencies, it's huge, isn't it? So it's now looking like this to you guys. It looks small at low frequencies and then bigger at high frequencies. So that's what the 0 at the origin is doing. It attenuates low frequencies and exaggerates or amplifies high frequencies. Is that making sense? Maybe I will, how much of this do we, so where did you get? Did you at least get the time constant form? Because this is pole 0 form, isn't it? All right, so if I can ask you to not write any more on your paper, then I can see where you got to and then where we need to focus maybe our attention in additional lecture material. But, well, what? So can we sketch this? So don't write any more on your paper. Say time's up if you want to write on your paper, but just draw a line so that I can actually see how well you're doing with this. First thing I would do is I would put it into time constant form, and I selected it so that the bottom poles were located nicely, and that when you factor those out, you end up with 1 when you multiply them together. And we now have 100s over s over 0.1 plus 1, s over 10 plus 1. So now if we looked at this in terms of this guy, and now I could say, what's the DC gain of this transfer function? What's the DC gain of this transfer function? 0. This one you can evaluate, can't you? You can plug s equal to 0 and you have a DC gain of 0. So this is going to annihilate constants. You put in a constant and it's not going to get out to the output. That's what that means, right? You're filtering DC dramatically. You have a DC gain of 0. But you do have this piece that will amplify all frequencies. And so your constant term will give you 20 log of 100, which is 20 log of 10 squared, which is 2 times 20 log of 10, or 40 dB. So now we have 40 dB of gain due to the constant piece, and now we have a 0 at the origin. That'll give us a positive slope, and we will have 2 poles that kink at 0.1 and 10, or break at 0.1 and 10. So if we put those together real quick, we'll have action occurring. Whoops, that's my axis. So let's say that this is now 10 to the minus 2, 10 to the minus 1, 10 to the 0, 10, and 100. And I have my 0 dB, I'm sorry, That's my 0 at the origin. Here is my gain piece. This is now 40 dB. I have a break due to omega equal to 0.1, and I have another break at, was it 10? So this one now is going like this. So that if I put all of those pieces together, now you have to kind of keep track of what's going on, just like we did before. And I like to sort of go as far back to the left as it makes sense. And in this case, I want to go all the way back before I see any of these breaks to maybe here. And I say, okay, where can I start my resulting plot? Well, this guy's contributing minus 40. And that one's contributing plus 40. So I can actually start my plot right here at 0 dB. Does everybody see that? And which way, what will I do from that point? Will I go flat? Will I go up? Will I go down? Is everybody okay with me starting at 0 dB? Actually, I'm not starting. I'm actually coming up, but that's where I'm crossing. Yes? And I'm going up. So now I want to go up 20 dB per decade until I reach a break. And at that point, I'm going to be flat. And then I will come down and I'll be parallel to this last curve, and that should have gone through 0 dB at 10 to the 2, which is 100. So there's your magnitude sketch. I'm sorry? Will I be parallel? If I look at what's happening at high frequencies, what's my slope at high frequencies? I have plus 20, minus 20, so those cancel, minus 20. So I'm coming down at minus 20 dB per decade, and that's what this is supposed to be. So my sketching may not be very accurate, but it should be that I'm sloping at minus 20 dB per decade. And I could even ask that question. I could say, what's the slope of your magnitude plot at low frequencies? And what would you tell me? Plus 20 dB per decade. Does that make sense? I could say, what's the slope of your magnitude plot at high frequencies? And you would say, oh, it's minus 20 dB per decade. And that's because you have one more pole than you have 0. You have 2 poles and 1 0, so you have one more pole than 0. You should be sloping like one pole at high frequencies. Let's do the phase sketch. Or are there questions on the magnitude plot? That's a bandpass filter, isn't it? You're passing frequencies in a band from 0.1 to 10. Those are the frequencies you're favoring. So it's a band pass. You're annihilating or stopping or trying to block frequencies below that and above that. Question? Yes, so the question was, when you're sketching individual pieces, is it possible that your slope could be something other than plus or minus 20? And the answer is yes. Okay, let's move on. Why is that? Let's say that I had 2 poles at the origin. Well, let's be consistent with this. Let's say instead of 1 0 at the origin, let's say we had 2 zeros at the origin. Now we have an s squared, don't we? So instead of going up at 20 dB, we would be going up at 40 dB per decade. Meaning we would still go through this point, omega equal 1, 0 dB, but now we would be way down here at minus 40, 1 decade before. 40 dB below that, 1 decade before. So now we're at minus 80 dB at 0.01. So this is sloping now at 40 dB per decade. If we had, and this is what will happen if you have quadratic factors, now you have this 2 factor, and you will be sloping at 40 dB, either plus or minus, depending on whether it's a 0 quadratic or a denominator or pole quadratic. It's all in the power. It's all in the power. Yes. that making sense? And what are we doing with quadratics? We are going to approximate those in this class. It's not what's really happening, but in this class, just to get us sketching, we're going to roll that all the way around. We'll keep it on a string and just keep the natural frequency the same and roll it down to become two real poles. Instead of two complex conjugate poles, we'll roll one down and one up, and they'll both be real, and then we'll treat it as an s over omega sub x plus 1 quantity squared. And there you'll get that 2, that power, and that will give you a different slope. If it's a pole, it will be minus 40 dB. If it's a 0, it's plus 40 dB. Does that help? Other questions on the magnitude sketch or plot? Is this making sense? Now you're actually going to be able to design because you know how to create transfer functions that have that shape. Yes? You now know that if somebody says, oh, I've got something coming up from way down below at low frequencies and coming up, that's a 0 at the origin. And if it's going plus 20 dB, you know you have 1. Then you say, oh, it flattens out at 0.1. Oh, that means I was going plus 20 dB, now I'm 0, so I must have introduced a minus 20 dB per decade slope. That corresponds to a pole. And that pole must have happened right at omega equal to 10 to the minus 1 or 0.1. So now we are designing, so you can sketch on your napkin some Bode plot, and you can create the transfer function. You can do system identification. You can identify the system that corresponds to that Bode plot. Once you have your transfer function, you should be able to, maybe with a little more study of chapter 14 and 15, realize that transfer function. So now you're doing system realization. You can realize that transfer function as a circuit. You can build it. Now you can go visit Josie and have your Bode plot. You can go, Josie, and get some parts, put them on a breadboard, and say, look, here's my Bode plot. So you've gone from napkin to frequency response sketch to transfer function to filter, realization. And we've done that in under 70 minutes today, right? You have a lot of skills in your toolbox. You just need to know how to use them. Let's do the phase. We have plenty of time to do the phase. I know you're getting anxious. I can feel it. Now, what do we have contributing? What did the constant contribute? 0, so we don't have to do anything. What did the 0 at the origin contribute? Plus 90 for all frequencies. That's the 0 at the origin contribution. What about the pole at 0.1? It's going to be contributing minus 90 degrees over a 2-decade span, and that 2-decade span needs to be centered right at the break, and the break we said was 10 to the minus 1. By this point then, it's contributing minus 90 degrees, and it's straight line from 0 degrees to minus 90. That's due to the pole factor at 0.1. The pole at 10 kicks in at the same where the other one kicks out, and it turns off at a decade beyond that, and so it will now be right there. Is that making sense? Now all we have to do is add them up on these vertical lines at each frequency, because these angles add and subtract because they're products in the transfer function. Doing such, we start at 90 degrees until we reach 0.01, and then we're sloping down. And now what happens? We continue with exactly the same slope, don't we? We kicked off the slope due to the first pole, but now we have a second pole that just catches back up. And so this one is going to lay right on top of that, and that's now what our our phase looks like of h of j omega. Meaning at high frequencies, what's our phase shift? Minus 90. At low frequencies, what's our phase shift? Plus 90. Is there a frequency where our input waveform is aligned with our output waveform in the sinusoidal steady state? There's just one frequency, isn't there, in this straight line approximation, and that's right at omega equal to 1. And this is what you should see if you sketched the frequency response or Bode plot in MATLAB. You should see this straight line, or it will be a more exact or precise picture, but this is the straight line approximation. Now, do you need to go buy about, I don't know, 2,000, 3,000 napkins so that you can practice? I'll see you on Tuesday.